Welcome to the fastest way to learn data structures and algorithms with premium revision material. Today, we dissect LeetCode 427, construct quad tree. If you want compression, recursion, and tree structure in one interview problem, this is the blueprint companies love. Let us read the problem statement together. We get an n by n binary grid made of ones and zeros. The side length is always a power of 2. We must build a quad tree. Every node either stores one uniform value for its entire square region as a leaf, or it splits the region into 4 equal quadrants, top left, top right, bottom left, bottom right, and points to 4 children. A leaf has isLeaf true, and val matches that region, 0 or 1. An internal node has isLeaf false. If every cell in the current block matches, we stop splitting and compress that whole block into a single leaf. Picture a satellite photo of a city park. When the entire tile is grass, you store one green label. When one corner has water while the rest is grass, you zoom in and store 4 smaller tiles. Quad tree construction is that zoom and label pattern, driven only by whether the current tile is uniform. For our strategy, we use depth-first recursion on the current square. The helper knows the top left corner row and column, plus the side length. If the side length is 1, we read that single cell and return a leaf. Otherwise we split the length in half, recurse on the 4 quadrants, then try to merge. If all 4 children are leaves and share the same value, we replace them with one leaf holding that value. If not, we build an internal node with those 4 children. That merge rule turns a naive full split into an efficient structure when the image has big uniform patches. Now the dry run. Look at a 4 by 4 grid. Row 0 reads 1, 1, 0, 0. Row 1 reads 1, 1, 0, 0. Row 2 reads 1, 1, 1, 1. Row 3 reads 1, 1, 1, 1. At the full 4 by 4 window, we are not uniform because we see both 1s and 0s, so we split into 4 2 by 2 blocks. First block, top left 2 by 2, is all 1s, so we return a leaf with val true and isLeaf true. Second block, top right 2 by 2, is all 0s, so we return a leaf with val false and isLeaf true. Third block, bottom left 2 by 2, is all 1s, so that is another 1's leaf. Fourth block, bottom right 2 by 2, is all 1s, so we return another 1's leaf. When we return to the parent, we ask, can we merge? The 4 children are all leaves, but their values are not identical because the top right block is 0s while the others are 1s. We cannot merge. We return an internal node whose 4 children are those 4 leaves. That internal node is the root of our quad tree for this example. Now let us read the Python code. We define a helper called build that takes x, y, and side length L. If L equals 1, we return a node from that single grid cell as a leaf. We compute half as L divided by 2. We recursively build top left starting at x and y, top right at x and y plus half, bottom left at x plus half and y, bottom right at x plus half and y plus half. Then we check merge. If every child is a leaf and every val matches, we collapse to one leaf. Otherwise we return a non-leaf node with 4 pointers. For complexity, time is O of n squared for an n by n grid because we may inspect cells when checking uniformity during construction. The recursion depth is O of log n, so call stack space as O of log n. Extra node objects can grow with the pattern of splits. And that is construct quad tree, mastered for your next on-site. If this helped you today, like the video, subscribe to Leo Academy, and share it with friends who are preparing for coding interviews.